Welcome to the third talk of Human Factors in Design. I'm Joseph Giacomin, and today we'll be talking about the topic of biomechanics. So what's biomechanics? Biomechanics, first of all, it's important to clarify it's an interdisciplinary field. It tends to be a little bit the science of how the human body works mechanically. It's a bit a cross between mechanical engineering, biology, medicine, and it looks at the various structures of the human body, the bones, the muscles, the tendons, the ligaments, and so forth, the organs. It looks how they operate from a scientific, engineering, somewhat mechanical point of view. So, where does this come from? Again, it's tricky to identify when something, a field of endeavor, actually starts, but many people would suggest that we owe quite a bit of gratitude to Giovanni Borelli, who in the 1600s performed a lot of studies of the motion of animals. He wrote a book called De Motum Animalium, which clarified how bones and muscles in different types of animals, dogs, cats, cows, and so forth, how they operate. And what was the point of view that was taken at the time in a preliminary manner, and today tends to be very much the standard approach? Well, today we tend to think of bones of any animal's body as the structural members. They're the most rigid part of the body, so we think of them as the structures, the beams, the mechanical parts that hold the thing together. Articulations, meaning joints of the body, are load-bearing surfaces which permit movements, either sliding or rotational movements. Tendons, we tend to think of them in the same way that we think of cables on a bridge. They transmit forces from one place to another via a lengthy, thin pulling motion. Tendon sheets, we tend to think of the tendon sheets of the human body that permit the tendons to move without too much friction. We tend to think of them in the same way we think of pulleys in mechanical engineering. Muscles, we tend to look at them as being the motors, or the dampers, or when we're trying to hold something in place like a weightlifter, they would be considered in that instance the lock, which holds the body position in place. Flesh tends to be considered mostly as a mass element, a mass loading, or a volume element of the body. Nerves, neurons of the nervous system, we tend to think of them very similar manner to what we would think of electrical control systems in a machine. They are via electricity, the manner by which the body turns things on and off and changes the amplitude of a motion or the speed of a motion. And the organs, such as the liver, such as the kidneys, such as the lungs, heart, and other internal organs of the body, generally we think of them as producers of energy, and we'll talk about ATP and energy later in today's talk, or the consumers of energy. So the bones, these are the structural members. The adult human body normally has 206 bones. Children will be born with more of them, but over time as they get older, some of these bones will either fuse together or disappear, and as the body grows, the number gets to be less, and the adult tends to have 206 in the body. They are, as we already said, they are the beams. They are the structural joints. They are the things that hold us together and permit us to do external work like lifting, pulling, pushing, holding, and so forth. Now, a very important thing from a human factors and ergonomics point of view, it's very important to clarify that bones have a preferred direction of use. Evolution over many millions of years, certainly hundreds of thousands in the case of humans, but probably, since we share these characteristics with animals, over millions of years, bones have developed to be optimal and to work best in certain ways. Now, this is a diagram with some engineering numbers. Please don't be too concerned about the units, which are megapascals, and the way in which they were measured. Roughly what this table shows is they took samples of human bone, they put it in a traction machine in the lab or the workshop and pulled it slowly, measuring the force displacement curve. Those of you with an engineering background will be familiar with traction measurements, and pulled it until it broke and measured the relationship between the force and the displacement. And in the linear part of that, which is quite extensive, what was calculated was the Young's modulus, the value listed in the table as E. The table shows two values for E, longitudinal and transverse. The difference being, in one case we pulled the sample longitudinally along the sample until it eventually broke, and the other case we did it laterally. We pulled it apart side to side. Please note that the numbers in the table are very different for the two directions, and the longitudinal, when you pull a bone like a leg bone till it breaks, you can see that the Young's modulus is almost twice as much as when you do it laterally. And this is suggesting that particularly the long bones of the human body have evolved to carry the loads and do their job in the direction you're expecting to do it. And what do people do? They stand up and they walk around or run around with gravity pushing them down. So the long bones of the leg, the long bones of the arms are very good for exchanging or resisting forces along their length. Very bad when you hit it laterally. And this is why in sports such as football, there's such severe regulations that you can get a red card in football if you kick someone's leg or if you kick someone's ankle in a transverse direction, because the bone is not as strong in that direction, and it's very easy to have a fracture and to hurt a person. So in most sports there are very severe penalties for running into someone or bumping someone in a transverse manner as opposed to a longitudinal manner. Very important characteristic, because in human factors we will try as much as possible to design things to permit people to lift them using their arms and their legs in a longitudinal manner, because that is where we're best at carrying the loads. Now, besides the bones, which are the most rigid, they do deflect, they do bend a little bit. They're not perfectly rigid, they're not made out of diamond. However, they are the most rigid part of the human body. After them, there's another set of load-bearing mechanical materials which keep us together and help us to transmit loads and do external work and so forth. But these are slightly softer, not as strong as the bones, and these are the connective tissues. In the image we see the three main types: tendons, ligaments, cartilage. Three types, the kind of thing that's important to memorize and to be able to discuss, for example, on an exam. Cartilage. It's a smooth, tough, flexible material. It's made out of collagen. There's a lot of liquid, a lot of water in the thing. It's a bit spongy, not nearly as hard as the bone. However, the cartilage is found in a wide variety of parts of the human body. Cartilage is found between one bone and the other in the back as the intervertebral disc. Cartilage are the load-bearing surfaces, as you can see where it says hyaline, between any one bone and another that meet. If they can rotate and move one respect to the other, the cartilage is the thing that's permitting the flexibility and the low friction capabilities to permit the rotation, permit the movement. And one very fundamental type of cartilage is the elastic cartilage of our vocal cords. Right now, my lungs are pumping out air. They're pumping them over the vocal cords, which are vibrating and creating a frequency disturbance That frequency disturbance is then shaped by my tongue and my mouth and my teeth. It comes out as oscillations in the air in the room, gets picked up in this case by a microphone, and it's what you're hearing right now as I talk. So without flexible, tough, resistant, that can resist possibly almost a whole lifetime, cartilage, it'd be very difficult to have a stable means of communication. Ligaments. Ligaments are connective tissue. They're bundles, again, of collagen. It's always collagen in the three connective tissues. They are the pieces of connective tissue which connect together the bones across a joint. One bone and the other bone, the one below and the one above, are connected by a ligament that keeps them together, because otherwise when we move we would have the possibility to slide off or slide out. Ligaments maintain the tension and keep things together so we can have motions without the upper bone and the lower bone separating. So ligaments are very important at the knee, at the ankle, at the wrist, at the elbow, at the shoulder complex and so forth. Everywhere we have large movements and rotations of one bone with respect to the other, we have to thank the ligaments for keeping the tension and keeping them together. And when you're playing a sport and you twist your ankle, or you twist in tennis your elbow, and you stretch too much the ligament and it gets a little bit longer, a little bit damaged, possibly even with a small rip or crack, you then have an articulation which is not nearly as stable, and they could pop out from time to time and have a separated shoulder or a separated knee or a separated elbow. So ligaments incredibly important in sports. When they get a little bit too long or somehow damaged, they are very quickly sent to hospital for repair, because otherwise the sport becomes difficult to perform. Tendons. Tendons are present in many, many points of the human body. The image is showing one very obvious place where tendons are very important. Tendons will connect from a muscle tissue, to a bone. So what it permits is a muscle, usually a quite big one, to operate on a bone somewhere at a distance through what is conceptually a cable. So if we look at the human foot here, we can see that the bones of the toes, which are relatively small, just like the bones of the hand, they're operated by what are relatively large muscles much further up, in this case up by the ankle, pulling on the tendons across a tendon sheet. Why did Mother Nature, why did evolution provide us with such tools? It's because something like a finger, to be able to play the piano and move them very, very fast, you can move them almost as fast as 20, 30 hertz, thus blurring the vision of it. The best pianists, sometimes hard to see just how quickly their fingers are moving. We would not be able to move these bones and the associated tissue with a muscle that was small enough to fit right there where the bone is. But by having a very large one further up and pulling it through a thin and lightweight cable, we can generate great speeds, great velocities by moving a low inertia piece with a very large force generating muscle through the tendon. So the tendons permit us to optimize the placement of the motor over here, the small end effector or actuator over there, pull it very quickly and very strong, because I don't have to put them together and I'm not held back by the mass of the muscle being actually loading the end effector itself. So it's Mother Nature's way of optimizing things to help us to compact our bodies and be stronger and faster than we would have been if bones and muscles were always having to be one next to the other, attached to the other. And these connective tissues, the ligaments and the tendons, they are not nearly as strong as bone. Again, in this table, don't be too concerned about how they were measured or the engineering units, but they are in the same units, megapascals, And you can see that the numbers, whether it's in compression or shear, for the tendons and the ligaments, they're much smaller usually than what you have for the bone. So they're softer, not as strong, but they're also tougher and more flexible and more rugged. So they permit motion, they permit relative motion, and they can take many thousands or millions of cycles of use without having a fatigue failure. Whereas the bones are a little bit more rigid and more subject to repetitive use failure, where they can crack from using them over and over at work or in sports. The spinal column, the most important of all the bone structures, the most important of all the motion structures of the human body. The spinal column is a very complex device, 24 small bones called vertebrae. Between each bone and the next one is a nice, large, flexible cushion made of collagen, again, made of cartilage. It has its own name. It's called the intervertebral disc. The spinal column, perhaps we don't stop to think of it nearly enough, but it permits us to turn to one side, turn to the other, bend over to pick something up, bend over to reach the ceiling to install the light bulb. A large amount of what makes us a human is possible because we have this quite flexible spinal cord, something many insects do not have due to their exoskeletons. It permits us to perform very complex types of motion and thus very complex types of work. The spinal cord, by standard and by custom, is divided into 3 sections. The top part up here is what's shown on the diagram. It's referred to as the cervical region of the spine. The more central area is called the thoracic section of the spine, and the lower part near the pelvis is referred to as the lumbar section. The number of vertebrae in each section are given here on the diagram: 7, 12, and 8. Then at the very bottom there's the sacrum, and at the very end of this, some people a little bit more pronounced, some other people less pronounced, there's what's referred to as the coccyx, which is the evolutionary remnant. It's what's left after thousands, perhaps millions of years of evolution. It's what used to be the base of a tail. So human beings in their evolution lost a long time ago the tail, but we still have a little evolutionary remnant of it, which is this rather sharp bone, which is incredibly important in the design of chairs or automobile seats or airplane or train seats, because it's one of the points which actually sits on the cushion of the chair or the seat. Thus, it's a pressure point which the seat has to be designed, given a shape, to be soft and balance out the pressures at the 3 main points of contact. And this is one of them. And depending on how sharp it is, you will get greater or lesser stresses, and that can be a feeling of discomfort if the stresses in the foams go up. So a very important point in seat design. Now, a very important thing that all human factors and ergonomics experts are familiar with and think about on a routine basis is the fact that the spine is not straight. It's a curve. It looks a bit like an S. What you're seeing now in this diagram is the natural, relaxed state of the spine when you're standing up outside at the park, perhaps walking around in a relaxed, natural manner. So what do we have in its natural, neutral position? We have a set of curvatures. We have what's referred to as kyphosis and what's referred to as lordosis. The 2 forward curvatures in the lumbar region at the bottom and then the cervical at the top. In this diagram, what you have is someone whose face is looking to the left. They're walking to their left. In the diagram, you have 2 forward curvatures in the lumbar and the cervical regions, and you have a backwards facing curvature in the opposite direction in the thoracic region. All three are very important. Whenever you flatten and straighten the curve of any of these three of the spine, it leads to pressure loadings on the intervertebral discs, which you have pressure sensors inside of them, which tell your brain, hey, it's not so comfortable, I feel a bit discomfort here, a bit of pressure on my back, and it's not comfortable, and over long periods of time, flattening of any of the three curvatures can lead to eventually back problems, damage, permanent pains, and so forth. Of all the three, ergonomists and human factors experts tend to take a very great interest and spend a lot of time designing chairs, seats, desks, workstations, robotic platforms, and so forth to optimize the curvature of the lumbar region. The very bottom of the curve is the one that tends to be flattened the most when you're sitting in your office chair in front of your computer much of the day, hours and hours and hours. That can lead to back pain very easily if there's a lot of flattening of the curvature. And as I said, between each of the vertebra, there's the cushion or intervertebral disc, which again is cartilage. It is again, of course, collagen fibers. It is again a soft, tough, low friction, spongy, because it's full of water, material. Because it's spongy and full of water, it means that when you flatten the discs and compress the intervertebral disc because of the flattening and straightening of the curve, you end up pushing a lot of liquid, a lot of water out of the spongy cartilage. It gets compressed, it gets squished, it gets squeezed together. In that condition, it's very easy, begins to dry out a bit. It's very easy that if you do a sharp movement or try to lift something, it could break, it could crack or tear or have a little damage to it. So sitting a long period of time in a position which is not natural to the spine means that then whatever you do to lift and push and grab, the loadings crossing that area, there is the possibility of the damage. And that's why so many people, after spending an hour or two on the sofa or in the office in their chair in front of their computer, they get up, they lift something up, and they hear crack because one of the vertebrae, either at lumbar 4 or lumbar 3 or lumbar 5, one of the vertebrae between those segments may get a small damage, and that's how you get problems, herniated discs and so forth, that need to be looked at orthopedically. Now, the behavior of the spine and the kinds of things that you need to think about as a human factors experts can be surprising because not everyone is fully aware of these circumstances, but they're very important to show. One set of images that I'm using here is taken from a relatively old study, 1964, a long time ago, but it's a beautiful study because very simple, very well illustrated, very well done, carefully done medical study, and it illustrates the points we need to make here about human factors considerations. These experiments, Nakinson and Morris, 1964, what did they do? They took some people at hospital, they rounded up some volunteers, some patients, and they asked them to participate in a study. And what did the study involve? The study involved inserting what's referred to as a balloon catheter, which is a tiny little needle with a bubble of air or gas at the tip. They would put anesthesia around lumbar 3, 4, or 5. They would then make sure the person doesn't feel any pain, and then arrive with this very small needle, tiny little needle, and actually insert it through the skin into the intervertebral disc, such that the little ball balloon at the end of it was feeling the pressure that was occurring in the disc. And they then asked the people to stand or sit or roll over or move or perform various motions such that they took up different postures. And they had a little recorder coming off the needle, and they could see the pressure that was being recorded in lumbar 3, lumbar 4, lumbar 5 intervertebral discs, and they could see what's the effect of different positions of the body on these pressures. Which positions of the body are actually going to lead to lower pressures, which means less chance of damage, less chance of pain, less problems for the back. And amongst the sitting positions, they also, to make it more visible and clearer as a recording, some of the positions and some of the tests involved also holding weights in your hands just to load it up a bit and see it a bit better. And this is the result. Here are a set of postures or positions of the human body with or without additional loadings. And here is, on the y-axis, a normalized measurement where 100% was taken to be the natural, relaxed, Mother Nature's typically preferred position, which is standing up, walking around, as we did many hundreds of thousands of years ago, running around the savannah. We would have been standing and running in the vertical posture. That, whatever pressure the needle gave there, they said, well, let's take that to be 100%, and let's see if the other positions give us less than that or give us more than that. So if we look at the positions, take a look what's going on. Standing up outside in the park, talking to your friend, is not so much pressure in the L3 intervertebral disc. It's not even that much more than laying down on your side on the sofa watching the football match on a Saturday afternoon. It's about 4 times laying flat on your back when you're asleep at night, but laying on your side's very close. But take a look at those measurements towards the right of the diagram, which are about sitting down the way we do today, thanks to our offices and computers and automobiles and buses and trains and aircraft and park benches and so forth. Take a look what happens when we sit down. Just sitting down with no loading whatsoever, doing nothing, 140%. That's 40% more than standing up. Most people would probably think that sitting down will relax your back and not add loading. This is actually loading it up by 40% more. Bending slightly forward like this, rather than sitting a little bit more straight like this, bending even just a little bit forward almost doubles the pressure on the L3 lumbar 3 intervertebral disc. If I then hold something in my hand, some weights, pressure goes through the roof. So this is very important to consider. In human factors and ergonomics, we're always very sensitive as designers to the fact that asking a person to sit down for lengthy periods of time means putting the back in an unnatural, often unhealthy situation. So we have to minimize how long people do that. And that's why when you drive an automobile for a living, such as a taxi driver, a police driver, an ambulance driver, and so forth, there are relatively strict guidelines about shifts and breaks and how many minutes a break must be, because if we don't make the driver or the passenger get up and spend 10 or 15 minutes break standing up, leaving the vehicle, we have a risk that after 2, 3, 4 hours of vehicle use sitting in something's between 140 and 185% loading of the vertebral disc, we have the risk of over days or weeks creating a medical condition in the person's back. So very important ergonomics. Seat design has been the subject of thousands, literally thousands of studies, because it's very easy with a poorly designed seat to hurt somebody's back over a period of time. Seat design is very well catered for with all vehicles and all environments, and we're very conscious of the fact that in a factory setting, in a work setting, we have to be very careful about specifying how many hours in what positions the person has to work. Now, moving away from the back itself and its functioning and this huge risk if you don't maintain lumbar lordosis and keep those loadings fairly low in the lower region of the back, let's take a look at the other aspects of biomechanics. Let's look now at some of the other things. That is a huge issue. Now let's start to look at some of the issues, some of the other issues, the sources of some of the other issues. Muscle tissue. Muscle tissue accounts for about 40% of the human body weight, and it's broken down into three types of tissue. One is skeletal. That's the one most people think about. It's the one permitting me to move my arm, permitting me to move my fingers, and so forth. There's smooth muscle, which is a little bit less in most people's thoughts. The smooth muscle is what we refer to when we talk about the heart beating. It's not something I'm directly thinking about. It's part of the nervous system that's involuntary. It's somewhat only indirectly controlled by my brain. Things like blood vessels, certain characteristics of the liver and other organs, they were all examples of smooth tissue. Cardiac muscle is rather specialized. It's configured a little bit different from any of the others. It's got very short, very sharp fibers. Thus, it's been given a category all of its own. So it is a type of smooth muscle, but it has a physical structure which under the microscope is very, very noticeable, very specific. So it's given its own name. It's built up of short and thick and dense mesh of fibers. And of course, as we know, it's responsible for the contractions and pulsations of the heart. All tissues, whether skeletal, smooth, or cardiac, it all comes down to actin and myosin. They are two fibers which are proteins, like most of the human body is proteins. These fibers, they work in a chemical manner. They have physical configurations where they can ratchet onto each other if the right chemical reaction is provided to bring them together and to link them. Thousands or millions of these fibers are packed into bundles. When the brain says to move and some chemicals are released, these things ratchet onto each other, and as they ratchet, they pull each other just slightly forward, one respect to the other, and this is what permits us to move. All movement is the relative motion of thousands, probably hundreds of thousands, possibly millions, depending on the muscle involved, of these actin and myosin fibers. And what controls the movement? How do we make things move? How do we get an idea from the brain up here down to the finger over here and say, okay, finger, go down now, or finger, go up now? This is electricity. It's electrochemical signal. It's an electrochemical action modulated by the neurotransmitter acetylcholine. We have what are referred to as motor neurons, which bring the electrical signal down from the brain. So once the brain started requesting something in certain areas, started to be active electrically, the electricity propagates down along the motor neuron. It reaches the muscle pack, where lots of actin and myosin fibers are packed together as muscle tissue. It reaches the outside of that, and it's connected the two things together through what is referred to as a motor end plate. So just in the way, in a similar manner, those of you of an engineering background might be familiar with engines, such as petrol engines, and we have the battery and we have electricity, and the electricity goes to the spark plug, and the spark sets off a chemical reaction of the mixture of the petrol and the air. Well, here we have chemicals in the muscle fibers between the actin and myosin. They're sitting waiting for activation. The brain sends an electrochemical signal down. It reaches the motor end plate. That electricity kicks off the reaction in that point, and the fibers start to move, and we get the muscle contraction that we're all familiar with and can see from the outside of the body. So in a very similar matter, nothing that human beings have ever invented hasn't already been present in nature, in the same way that mechanical internal combustion engines use electricity to control the chemical process occurring in the cylinders. The human brain controls via electricity the chemical actions occurring in the muscles. And the chemicals in the muscles that are responsible for this conversion, that brings these fibers together and produces the motion, these chemicals are referred to as adenosine triphosphate, ATP. That is the starting configuration. That's like the petrol in the tank of the car. And when the electricity arrives and creates a stimulation, it breaks down from the ATP, the triphosphate. It breaks off what you see on the left of the diagram, which is the phosphate group at the end, which is not held on very strongly. That can be broken off by electrical reaction, and it breaks down to ADP, adenosine di-2 this time, phosphate, because we lost one of the phosphate groups. This chemical, which is loaded up with an unstable phosphate at the end, which can be stripped off, this chemical, its conversion goes on over and over again. Electricity breaks it. The breaking brings together the muscles to produce work, external work of the body, and then some other chemicals come along and build it back in by sticking the phosphate group back on. So we have a constant cycle of the petrol is broken down, and unlike the cars, the petrol gets reassembled by adding another phosphate with some additional chemicals which loan the phosphate to it and get it back to be ATP again. So tri goes to di and some motion of the muscle, then we fix the di back to the tri, and it's a cycle that goes round and round as long as the chemicals can be provided by the body to sustain the reaction. So as I've said, ATP, adenosine triphosphate, and of course there is water, H2O, in the environment surrounding the muscle fibers. That, thanks to the electricity, breaks down to ADP, plus the motion of the fibers. They moved, and that's energy, that's work output. We then come along later, millisecond or two, and we put creatine phosphate, one of the chemicals that can build it back up. Bit of chemical, the ADP, little bit of energy from other nutrients available locally, and we build it back up again to ATP plus again the water. So we have a cycle that goes around as long as it can be chemically sustained by the nutrients in the body. And this muscle action, the ATP breaks, we use it, we do things, run around, lift things, whatever, then we have to build it back up again. This can occur in different ways. For the first 20 or so seconds, if we look at the diagram in front of us, it says on the y-axis, proportion of the energy delivering process. So how much of the energy that's being used by the muscles, where's it coming from? How much of that is coming from what? And you can see on this diagram, we have proportion percentage on one axis, and we have the number of seconds from the clock, the watch clock, the number of seconds of the activity. So I lift a weight and I hold it for a couple minutes. This diagram is showing us where the energy is coming from to keep those actin and myosin fibers pulling on each other long enough to hold the thing up. For the first 20 seconds or so, we see a little curve which is referring to the creatine phosphate being present in the neighborhood, and the creatine phosphate is taking the ADP and bringing it back to ATP. So there's a chemical process using creatine phosphate, it's another chemical substance, which is locally available, and it lasts about 20 seconds. So when we're lifting a weight, we can probably hold it for 20 seconds regardless of how we're breathing, regardless of what we ate that day. There shouldn't be a huge problem to maintain the muscle contraction because there'll probably be enough creatine phosphate. From 30 to 90 seconds, there's a process called anaerobic, meaning without oxygen, glycosis, in which sugars are converted into chemicals, into the creatine phosphate to do the job and keep the ATP cycle going. But this process involves a byproduct. Part of the chemical reaction, the waste of the reaction, a waste product of it is what's called lactic acid. And lactic acid is the thing you start to feel when you're getting tired. If you've been doing a sport for a while and your muscles start to ache, That's the lactic acid which you're feeling. So for the first 30 seconds or so, no problem, creatine phosphate will do the job. The local reserves will keep the fibers in place. After that, the local reserves are gone. You've emptied the tank. So now you have to start producing the fuel, and the process called anaerobic glycolysis will produce it from sugars, but the byproduct is the lactic acid, which sensors in your body pick up and make you uncomfortable. So you realize you're starting to use your muscles a bit too much. And then after about 90 seconds or a little bit more, you then have a different process altogether. You have aerobic oxidation, different set of chemicals, slightly different set of chemicals, slightly different pathway. This is the pathway that you tend to have to use for endurance sports like the marathon. From 90 seconds onward, you are you're producing the creatine phosphate via this process of aerobic oxidation. And the byproducts of this, of course, are carbon dioxide and water as the byproduct. So you have three different sources of maintenance of the ATP cycle. They have different time scales and they have different requirements. So if you're a weightlifter, you will probably do everything within the first 20-30 seconds. This is about eating and preparing and sleeping and doing all your preparations to maximize your local creatine phosphate reserves. Sports, perhaps to some degree tennis and some other sports which have intermittent nature, moments of quite high activity followed by small gaps, well, it might be that your preparations have to target the anaerobic pathway and optimize your ability to use that pathway. And then instead something over long periods of time, such as, of course, the marathon, running the marathon would be the standard metaphor, the thing most people think about. Those that require long periods of time, that require oxidation reactions, well, that requires different things still. For example, to run the marathon, you might do quite a bit of training on your lungs to try to do exercises to expand whatever you can, whatever possible, your lung volume, because the reaction depends on how much oxygen you can take in. And if you can expand just slightly your lungs and be more efficient in your respiration, you can get more oxygen to the reaction. That would help. So, as we've already said, marathon, tennis, weightlifting, a small table showing you the breakdown of where research studies have indicated or measured where the energy, which pathway it's coming from. So you can see there's a mixture in different sports, and thus the food you eat, the number of hours you sleep, the preparations you make, and the training exercises you choose will be different depending on how long your muscle contractions need to be held for to perform appropriately that sport. And muscle contractions are interesting also in terms of the posture that you assume and the postural effects on that. If you've ever seen a video of the astronauts in space sleeping on the International Space Station, you will see that they're floating in space asleep with this funny position where most of their articulations are slightly bent over, and that is the neutral position of all those different muscles, of the legs, of the arms, of the back, of the neck, and so forth and so on. And this diagram is showing what we refer to when we say the neutral position of the muscle fibers and the lengthened positions or the shortened positions. If we look at this diagram has on the y-axis the percent maximum isometric tension, or the maximum force the muscle fibers can make when they pull, and we have the little drawing showing us how the actin and the myosin fibers are. So if we look all the way on the right, when the actin and myosin fibers are far away from each other and there's very little overlap, meaning my arm, for example, is like this, and I need to pull it back, In that position, you can see the percent force is relatively low. If I don't have a lot of fibers overlapping each other, I'm not going to get much force. But the other side of the diagram, which maybe is a little less intuitive, the other side of the diagram shows some very similar characteristics. If I've got my arm all the way closed and I have to try push open the window or the door to get out of a burning airplane, I have to try to push open the door from this position, I can't generate much force either, because the fibers are too much overlapped and they're interfering with each other and catching on each other and rubbing on each other everywhere, and we can't really generate much force from there either. So the neutral position, the one you would fall into when you fall asleep in absence of gravity, that position is the best one. So if I need to lift something, I'm not going to try to put something in my hand and lift it from this position, and I'm certainly not going to try to do it from this. I'm going to try to get towards the middle and begin the motion from a neutral position, the center of this diagram. Again, from a human factors and ergonomics point of view, this is incredibly important. When we design equipment, when we design automobiles, when we design anything that has health and safety issues associated, we want the people to be in a posture, be able to adjust the position, to be in a posture that when they start to pull something, they pull it with their elbow just slightly bent. When they have to push something with their leg, that they can do it with the knee slightly bent, or fingers on the keyboard, and so forth and so on. So to use the human body best, we must not put it ever in its extreme positions in one direction of motion or the other direction. We always have to try to go towards the neutral axis. And another aspect of force generation with muscles, which human factors people have to think about carefully in most applications, is this one. This little diagram has on the x-axis, going from across the page, this diagram has how much force, how much tension I can pull with, or how much force I can push with. And on the y-axis, it has the velocity or the speed of the push. So if I'm trying to lift something slowly, okay, my velocity is down here at the bottom, and it goes to a very high force. If I try to do it quickly, it's instead at the top of this diagram, and I'm not getting much force at all. So one of the characteristics of the human and animal muscle tissues based on actin and myosin is that if we move the muscles slowly and try to move slowly, we will be able to generate much more force. Thus we can lift heavier things or perform more difficult tasks that are heavier. We can produce much more force than if we're trying to do it quickly. And again, in safety situations, there's an emergency, you're trying to get out of the burning aircraft very quickly. The weight or mass of the release mechanism of the door can be usually influential in this kind of thing. If it's really heavy, it's going to be difficult to do it quickly. So again, physiological constraints on design, characteristics of the human body which greatly affect the design process are everywhere to be found as first principles in the biomechanics of the arms, the legs, the back, and so forth. And one additional consideration is endurance. How long can you hold the weight? If I'm a weightlifter, how long can I hold the weight over my head? Here's a set of diagrams where we have in minutes the time along running across the horizontal on the x-axis, and we have the amount of muscle strength on the y, and we have different curves. Curves for do some lifting, then have a little break at 10 seconds. Do some more lifting, have it again 10 seconds. Or do some lifting, have a 50-second break, then lift again. And if you look at the diagrams you see, if you get breaks and rests where the actin and myosin can release and the chemicals can move around in the muscle tissue and the ATP can be built up from the ADP, if you have breaks, and here the longer the break the better, you can generally produce consistently much more force. If instead you're getting no rest at all, it's just continuous production of force and work with your body, you're along the lower curve, and it's showing you can produce much less. So again, you think of factory settings and work settings and so forth. There's very, very serious and rather severe health and safety requirements in most workplace settings, particularly in things like factories that have physical activity, or mines, working in the mines, or other areas where there's much physical involvement in the activity. These requirements quite often stipulate very carefully a set of breaks and how many minutes as a minimum each of these breaks over the course of the day must be. And the reason for that, just in case you're ever curious, where did that come from? How did they decide that? It's this. You need to produce the breaks. Here, these are short breaks, but longer breaks are used as well. You need to produce the breaks so as to guarantee the force generating ability of the people's muscles, which then helps them to work safely without damaging themselves and without losing the grip on the control, slipping off the control, or something that could create an emergency or a danger situation. Couple final comments for today's discussion. Lever systems. Another aspect of the human body which probably isn't discussed nearly enough on television and by doctors and so forth. The human body is based on a set of lever arms. We have the arms, the legs, parts of the spine. Over and over again we find structures in the human body where there's a joint, a pin of some sort, and there's a long bone coming off it, and this bone can make quite a big sweep around that center of rotation. Well, this characteristic of the human body is something that in human factors we tend to think about quite a bit. It doesn't just appear out of nowhere. This is the result of thousands or millions of years of evolution in which speed was the important thing. In the distant past, speed and mobility were essential to survival. If you're about to be jumped by a wild animal, your only hope of saving yourself is to manage to run away. So we as a body, we as creatures have a body that's optimized for speed, for moving quickly. The legs are long, the sweep of the legs is quite ample, and the muscles of the legs are large enough to move them very rapidly. So we are very quick. Is there a drawback? Yes, there is. The drawback is to be this fast amongst the fastest of the living creatures, along with the cheetah and a couple of other creatures. The penalty we pay is very high internal forces, which we have to consider in ergonomics and human factors, because we don't want to ask people to lift loads which are particularly heavy, because we are particularly bad at doing it. So here's a little diagram, very simple, trivial, two-dimensional, simplified, almost absurdly so, model, but it's sufficient to illustrate the general principle, which is true. Here we have a simple model of the lower arm rotating around the elbow. If we put a weight, in this case, in this image, 7 kilograms, which isn't enormous, 7 kilograms seems a fairly reasonable size weight. If we put 7 kilograms on our hand and we take a look at what's happening at the elbow, so we have a distance, an adult male might have a distance of roughly 40 centimeters between the center of the mass that we're holding the thing and the center of the joint or the articulation of the elbow. The muscle which has to pull across the articulation and keep the thing in place so it doesn't drop, the muscle that has to pull it to keep it force in the other direction, action and reaction, the muscle will probably be pulling on the elbow joint at about 3 to 4 centimeters from the dead center of the joint. So, those of you with a mechanical engineering background will be very comfortable with the concept of summation of moments. So if we have something trying to turn it one way, which is the mass we're holding, and the muscles trying to pull it in the opposite direction to keep it level so it doesn't move, we sum the moments in the positive and negative, meaning the opposite direction, and we're going to end up with 7 kilograms times 0.4 meters. If it's not going to move and we're going to hold it steady, it's got to be balanced by some number x in newtons. Newtons is the unit of force, 9.81 meters per second squared. Acceleration of gravity times the mass gives us the force in newtons. We're going to have 4 centimeters, 0.04 meters times some number x is got to balance the 7 times 0.4. When we solve our little summation of moments equation, our little statics equation from engineering, we will find very quickly that we're talking about something of the order of 700 newtons force to balance it out. So we're finding something which is order of magnitude bigger than what we're holding to balance it out. So the message here, even though this is a very simplified model, it's close enough for the purpose. What we're saying here is to be fast, nature has given us long arms, long legs, lots of lever systems in the back. Everywhere in the human body there's lever systems in the small bones of the ear and so forth. All of these lever systems make us fast, quick, sensitive, if you wish to look at it that way. But it then means inside our body there's a lot going on. And to hold 70 Newton of force in our hand, we have to produce 700 newtons of force internally on the muscles just to keep from dropping it, 10 times more. What does this mean? This means when we look at a box to lift, when we look at a handle to pull, when we look at a knob to turn or something to rip, it doesn't take much force to create lots of forces, big ones, inside our body, and those are all things which could potentially create tears, rips, damages, and over time will possibly stimulate fatigue, fractures, and so forth. So, moral of the story, be very careful with anything requiring external work being done, force lifting, and so forth, because the human body is absolutely brilliant at doing things quickly, not so good at producing large forces. Lots of animals and other creatures are much better than us at lifting things, moving things, and pushing things. Similar discussion can be done for the back. Here's a simple lifting equation, simple two-dimensional, very, very, very basic, but again, sufficiently accurate to illustrate the point. If we're trying to lift the box, and the box is about 22 kilos, which roughly, if we multiply by 10 rather than 9.81, gives us 222 newtons of force need to be held in position. The muscles on the back that hold the vertebrae in place are 4 to 5 centimeters from the center of the vertebra. The vertebrae are quite large. When we do this summation of moments, 222 trying to tip us forward at a distance of 1 meter, 222 times 1 has to equal to something multiplied by 0.05 meters. We end up with 4,440 newtons. So to hold a 22 kilogram box, we have to produce 444 kilograms roughly in our spine. That is a lot of weight. 444 kilograms is the weight of a small car engine. That's what our muscles are holding up inside of us. So lifting is a very big concern. Any external work, pushing, pulling, lifting, turning, twisting, they're all very big concerns in ergonomic design. And we have very good tools for estimating things and looking at these issues. For example, there's books full of these things. I will only mention one because it's absolutely important to know this one. NIOSH, National Institute for Occupational Safety and Health in the United States, U.S. federal government agency. Over the last 30, 40 years, over a long period of time, they developed a set of what they refer to as lifting equations. And the lifting equation for something similar to the situation I just showed before of picking up a box is this one. Something times something times something times something times something times something equals RWL. Recommended weight limit, RWL. The box should not be heavier than RWL. And then there's a bunch of multipliers. How far in the horizontal distance is it from the center of your spine? How far up in the vertical distance? How many times every hour, the frequency multiplier, you're doing it? How strongly are you holding it with your hands, the coupling multiplier? Most of these multiplication factors are provided in the NIOSH standard in a table or a little diagram. So all you have to do is look at someone and see where they're lifting it and where they're putting it, how big a motion they have to make, and you can usually look up very quickly in just a minute or two all of these factors. You throw them all there, you get your hand calculator, you multiply them together, and the NIOSH standard will give you the recommended weight limit, and you'd be very surprised how small the recommended weight limit might be. Lifting boxes like an Amazon box to load it on the lorry, you might very easily find for average sized people with average sized boxes that box limits might be 20 to 25 kilos maximum, if not less. If they're doing it continuously, might be as little as 10 or 15 kilograms is the absolute maximum which would be permitted. So the NIOSH equations provide you a very quick and simple, rather two-dimensional way of doing it. There are more sophisticated tools, lots of computer simulations these days. Here are 3 mannequins, and this is not particularly recent. These images are from at least 20 years ago, but the software tools haven't really changed a whole lot, these particular 3. What we're looking at on the left-hand side is the tool that was called SafeWork. The middle was Ramses. The one on the right is called Jack. These are digital virtual mannequins. They're models of the human body. You can go on the menu, select whether it's the gender, whether it's male or female. You can select the size. You can select the body shape or somatotype, as it's referred to from a list of possible ones. And then you get a model which you can move around in your CAD system or your VR system. And there's a skeleton inside the model with muscles and joint centers and so forth. And the model can be used for lots of things which designers are interested to know as part of the design. For example, you can look when the person's bending over checking something in the engine bay of the car. You can take a look what would be the loadings in the lumbar region of the spine. You can look if the person's sitting at the in the control tower at the airport looking at the air traffic control display. You can check what the person sees from their eye with binocular vision. You can see what's in the center of their view field, what's at the fringes. You can see where you should be placing information displays to make sure the person doesn't have a difficulty in seeing them. The Jack simulation on the right is showing another thing which is routinely done, which is motion, in this case ingress and egress from an automobile. Can the person get below the roof and bend over to get down to the seat? Does the person get their foot trapped on a pedal as they enter the car? Is there any issue with holding onto the door latch mechanism while you move in or out of the car? You can check all of these things, and the idea being we check these with models and mannequins, because we can check the 5th percentile female, we can check the 95th percentile male, we can check any variety of sizes, shapes, and body structures, body types, and we can do all this before one of these prototypes is actually built. So we can check just how well, from a design point of view, things are working for people of different size, and maybe even from an inclusive design perspective, if we're simulating with these mannequins various forms of disability, we can check who it works for, how well it works for. We can do measurements like downloading the forces or the motions or whatever to a data files and doing analysis on it. All of this while the thing we're designing is still just a digital tool that's almost pencil and paper, and nothing has really been spent to manufacture anything. And with the increasing cost and complexity of everything we're making these days, anything we do might end up costing millions of pounds to the company to build a prototype and check it. So doing an enormous amount of work with the digital tools up front, including the human ergonomic and human factors work, is absolutely critical. And then finally, to finish up today's discussion, a couple of design classics, which are classics because of things related to biomechanics. One of them, the Nike Tailwind. When in 1979 this shoe first appeared on the market, looking at it from today's point of view, it doesn't seem so unusual. But when it first appeared in 1979, this was a revolutionary concept. We're not making the shoe anymore based basically on the materials we have available or some questions of the shape of the human foot. No, we're now making the shoe based on biomechanical calculations and considerations to try to optimize the force transfer from the human foot, from the different parts of the human foot at different stages in time during the motion. We're trying to optimize the force transfer between the human foot and the ground that we're walking on. So this shoe has gas-filled plastic membranes for the sole, which can be adjusted to different people and different body weights and so forth. And this is permitting us to optimize our running and sports performance by optimizing the force and loading transfers between our articulation, our foot, and the ground that we're moving with respect to, relative to, against. So this is an excellent example of something which the novelty and the unique selling point, the unique sensory proposition, the unique sales proposition is almost purely biomechanical in nature. It's not the other considerations that make this a revolutionary product. Another product whose great contribution to this day is of a very biomechanical nature. Yes, anything we design has many aspects and many characteristics, but what is the core innovation? In this case, again, biomechanical. 1933, for those of you who think these are more recent innovations, 1933, the invention of the X-brace wheelchair. The wheelchair that we all know and love today, that we're used to in any hospital anywhere in the world, that can be closed by bringing together the two sides as what's called the X-frame, which you can see underneath the seat area. There's a set of X braces with a sliding pivot. You can just bring the two halves of the device together to store it in the hallway or store it in the cabinet out of the way without taking up too much space. At the same time, once you open the X-frame and open the two halves up and lock it in place, you have what for 1933 is a rather sophisticated and rather adjustable device with easily moved by hand by the patient themselves, appropriately sized and positioned handles for if there's a carer pushing the device, an adjustable foot rest on each side to adjust to the person's needs with their lower limbs. So the X-brace wheelchair, which in hundreds of different variants is present everywhere still today in the world, is a low-cost, incredibly effective biomechanical solution. It's easy to push, both by the patient and the carer. It's got a number of adjustments that permit the adoption of appropriate postures for people with different conditions and different requirements. And it has that lovely closing mechanisms, which makes the storage so much easier and more practical, which is also a very important characteristic of a device like this. So that's our final design classic for today. Thank you so much again for your time and your attention. I hope that was of some use, and we'll be talking more human factors next week.